Hello and welcome back to the Hyperthesis. We are at the beginning of episode 41, which is our fourth season. In fact, this is an anniversary. Last year on May 19th, we came up with our first episode on acoustic black holes and Liam's work. Now we are not revisiting that for this episode, but we are talking about something kind of new. But my name is Feely.
I'm Patrick.
And I'm Liam.
So, it has been 1 year that we've been together. We took a little break between season to let us organize ourselves and catch up with our work. Also, that it's an end of semester end of academic semester, so we have some stuff to catch up on. So, are you guys have anything to talk about in terms of for an intro topic or update?
Yeah, during the break, I spent my time in Costa Rica, which is not as fun as it sounds. I was taking data for my research projects, and it was a little bit brutal. So the overall goal was to map where trees are, so that when we look at forests from space, we're able to tell which trees are located essentially within each pixel of an image. This is very important to know, so that way we can say, okay, there are X amount of trees of certain species in one pixel, and then in the adjacent pixel, there are a different number of species and a different number of individuals that's in that pixel, which is very important for trying to measure biodiversity and other aspects of a forest. In reality, we measured well over 10,000 trees using a specialized GPS device, or GNSS, Global Navigation Satellite System device. And it was 40 degrees usually, with direct sunlight and very hot. So it was an experience, to say the least.
I'm not seeing your tan at all. You look as pale as when you left.
I'm probably
Stop judging us.
So in these forests, the ticks are a giant problem, along with red ants, which will bite you and it hurts a lot, along with a whole bunch of other bugs. So I was wearing pants, long t-shirt, and sunscreen, and a massive hat just to stay out of the sun. For reference, the UV index every single day was 11, which is, I don't think we can even get that in Canada.
God.
Yeah. That's what happened when the ozone layer is not happy,
I think I would have died.
Well, and also a lot of things. The problematic thing is that things in the forest, the thing that would hurt you really bad or kill you, are really small. It's just tough. Like here in Canada, things that would kill you that look like it's gonna kill you. Like bear moves. Like, oh yeah, you're not gonna go near them. They're like these little ants in Canada. They're harmless.
Certainly, the insects were the worst, especially the ticks. But for example, they have jaguars. You don't really worry about them. They stay away from people for the most part. Whereas they have giant wasp nests on the ground. So if you accidentally step near one, they can feel the vibrations and they just go whatever's causing those vibrations. So yeah, small things will hurt you and can kill you.
So Liam, anything interesting?
I haven't been up to too much. What did I do again? I wrote an exam way back in like the end of April for my quantum field theory and curved spacetime class, and we still haven't gotten the marks back yet, even though they were due like 3 weeks ago or something. So classic professor things. But yeah, I've just been working. I've been catching up on some things. June is a pretty busy month for me. I have this like quantum simulator conference at Perimeter Institute in Ontario. So that's quantum simulators. They're kind of like an acoustic black hole is something you study that mimics a black hole. Turns out you can study things that mimic other systems. So a popular thing is that people study like superconductors and solid state systems, and those are really complicated because they're a bunch of atoms really tightly bound. So there's a lot of complex interactions happening. But you can mimic, you can like create ultra cold atomic systems and study kind of like fundamental physics, which mimics the solid state stuff, and that's a really popular thing. Although it's not something I've ever done, but I'm gonna go to a conference at Perimeter Institute with this and learn about it because it's kind of like that what I do, except instead of gravity, it's for solid state stuff. Um, then I'm going to Nova Scotia for a week to visit my family and friends and whatnot, so that'll be fun. And then I'm going to Italy for a week after that for a quantum gravity conference, which will be really fun as well.
Quantum gravity.
Or
Do
no,
you
it's not
even
quantum
do quantum
gravity.
gravity?
Sorry, no, analog gravity I meant to say. But the whole
Okay,
point of analog gravity is to like learn about quantum gravity. So I don't do quantum gravity, but I talk about it a lot and pretend that I do.
interesting. Huh. Quantum gravity is. I don't know where they're gonna go with quantum gravity. Honestly, I think it might work, but it's gonna be a while
Yeah,
we see any meaningful things out of it. I guess.
the whole point of quantum gravity is that you're trying to figure out a way to detect something that tells you about it. Because there's all these theories, but none of them really. There's a lot of theories, but you need experimental evidence. So that's kind of the hard part, is because the regime where quantum mechanics couples to gravity is really, really hard to get to, and it turns out like black holes are one of the only things we know that can do that, and we can't really. Black holes are so far away and so hard to get close to, and we can't really probe them, so it's hard to test. Anyway, going to avoid getting into a quantum gravity conversation today.
All right, then shall we get into our main topic then?
Bailey, what have you been up to?
I was okay. Yeah, I was gonna I tried to get away from that, but hey, I've been just wrapped up semester. I have a few projects that I finished up. I mean, one of my class finished, one of my community initiative project finished ish. So I think we are kind of made like final revision right now. Kind of. I'm not so sure actually. Just waiting for some feedback. But my class actually submitted grades on time, in time, and it came out on time. So I don't know what your problem was, Liam. Um,
The problem
but
is that the prof just hasn't marked it yet. I went and asked him like a couple days ago, and he's like, "Oh, I haven't marked it yet." It's like, come on, man.
I thought that they usually have deadlines because like people graduate, at the end of semester, right? And if you don't have grades, you might not be able to graduate.
It
But
turns out there's only like 8 people in this class, and all of them are not graduating. So I think he took that into account. Anyway,
well, I guess you can do that. But I started up my new projects. Have a couple, one summer student, and we gotta be hammering it out this summer. I'm trying to pushing one of the papers that I've been writing out, and it has been quite difficult to write, but it's worthwhile, I guess. So just nose to the grindstone. Not too much to talk about. It didn't go to any place fancy. It went to. Actually, I didn't really go anywhere, did I? Yeah, I'm just in the trench, just keep digging. But that's it for me. I think this summer might be more interesting things to do once it's warmer. I think yesterday I woke up, it's like 5 degrees outside. It's like, why? Why? But it is what it is. Anyways, I think we shall move on to the little main topic that I think I found. Well, actually, one of my friend's brother, who was in grade 12, finishing grade 12, asked me this question. He saw this theory, quote unquote, or video, a short video in video broadcasting platform, the ones that quite popular, the clock one, tick tick tock tock one, yeah. So that one, and it's an excerpt. Well, it's a short excerpt video from a Netflix documentary, or well, I mean, the Netflix movie slash show called A Trip to Infinity is about the power of infinity. And there is this thought experiment called the apple in a box that is quite interesting. So I think I explained to him in my view, but I think now I look into it more, they have actually pretty interesting background that I think we should talk about. So let me explain the apple in a box theory or apple in a box. So it's about infinite time. So let's say you have an isolated box, like a box that isolated from outside the world. Like you cannot access the inside, you cannot see it, you cannot heat it, nothing can permeate through the boundaries of the box. And let's say you have an apple, and you put apple in that box. Okay, so what happened? So if you leave the box for a very long time, right? So the apple would decay, normally just decay into smaller pieces. Maybe it just breaks down, the organic matter breaks down, and the apple would be gone, right? If you think logically, like follow normal reasoning. However, if you wait long enough, sufficiently long, all the molecules would break down into their elementary particles, and then even nucleus would break down into protons, neutrons, and those things also break down into subatomic particles. All these, smaller particles maybe break down to quarks, and all interaction making break down to the most fundamental particles. And we talked a little bit about that in the Heat Death of the Universe episode, where eventually things go to the most stable state or phase where you have nothing left basically, or just like some random fluctuations perhaps, or the most disordered state. However, if we have infinite time, because it is possible, though not very probable, that the particle would collide a certain way and come back into the previous state. They are accessible because quantum fluctuations. It's possible if you wait long enough that the apple would reconstruct itself, and maybe you open the box and you see the same apple again, because you give it infinite time, the apples, you'd have to reuse the state, right? There's a finite number of states that particle can be in. So if you give it infinite time, it had to reuse the states, and one of the reused states have to be the full apple. So that's an idea that emphasizes the power of the infinite over the finite, right? So if you have the finite number of states, even though it's so high, maybe 10 to the, many powers, 10 to the 100 or something, 10 to the 50, but that is a finite number. And if it's possible to revisit the state, then it has to revisit it at some point because you give it infinite time. And the theory that cover kind of the foundation of that is called Poincaré recurrence theorem, where it said like, well, you have some kind of dynamical system that, or dynamical means it just evolved with time, that has like this type of Hamiltonian or whatnot, or it doesn't have to be Hamiltonian, that being described by ordinary differential equation or differential equations. And if the phase space is volumetrically conserved, I mean, like the volume of the phase space is conserved, I mean, like you have like a finite amount of states available, then, through the dynamics, is have to reuse the states that's used before, and there's a certain amount of time that required to basically a guideline, like, well, once you reach this time, it will have to reuse the states because it used all the states, and then maybe you will reconstruct things.
So maybe I'm thinking about this not like ideally enough, but like when I think about putting an apple in a box where it can't interact with anything outside the box, I guess when I think of an apple decaying, I think of it's like it's fermenting and it's interacting with its environment a ton, and there's bacteria on it and stuff. So why would this apple decay if it's the only thing in the box and it's not interacting with anything? Because like you see in my mind, if you put like an apple in a perfect vacuum with nothing else in it, it should. I mean, at least within the time scales of. Again, this is all about time scales, right? But like just naively, if you don't think about infinite time, you'd think, okay, this apple's not gonna ferment or decay or it'll do some stuff, but because there's nothing else in the box with it, it won't like turn to mush. But I guess on the time scales are very very long. You get decay, you get like atoms decaying and particles decaying. So I wonder if you can comment on that.
All organic material have lifetime, like they don't last forever, and that could be because of entropy, maybe because interactions. Well, they might not even be able because interaction, because normal fluctuations also, like if you leave a rock for a million years, it might still be there. How about billion years? How about would nothing decay at all? Right? Like, because we know from elementary particles, they had some that have really short lifetime, some have longer lifetime, but they're not forever, right? Like these things don't exist forever. Even proton, neutrons, black holes don't exist forever.
Well, we don't quite know that one, but they shouldn't. But I mean, technically, I think. All right, maybe I'm wrong. I need to double check this, but I think so. Like radioactive decay and half life, like molecules decay into other things after enough time, and protons, we don't know if they decay, but there's some theories that think they do, and maybe some that don't. But I think when something decays, it's actually this is quantum field theory. I think it's interacting with um these invisible quantum fields that permeate all of space-time. Like for a hydrogen atom, an electron can spontaneously kind of emit a photon. Like it can hop up to an excited state and jump back down randomly on its own without anyone poking it with a stick. And you can only describe that with quantum field theory because it's interacting with these kind of with the vacuum of space. So I'm wondering if what is this like radioactive decay or things like that, which cause all these particles to decay down to nothing after a while. Are they technically still interacting with the vacuum or what?
I do just want to comment on something you mentioned quickly, which is proton decay. This was something I was fascinated by for a while. But just to mention it's still a theory. We don't know if it actually happens, but essentially it says that protons could potentially decay, but their half-life would be around 10 to the 31 to 10 to the 36 years. For reference, our universe is about 10 to the 10 years old, so very, very long half-life, more than really anything else that we know of. But again, given infinite time, then protons could very well decay.
Exactly, because like radioactive active material are recalled like unstable material, right? So they want to decay. But you could say proton is stable, but in the grand scheme of things, you look further, you say, well, are there any states that more fundamental than protons? Well, then they have lower energy states or lower entropy states. Oh, sorry, higher entropy states. Or well, I mean, talk about entropy is kind of hard when you don't have like um, averages. So if you look at one particle, entropy doesn't make any sense. But if it's one particle, it would want to go to the most stable, right? Like if you think of the conventional way of looking at time, and proton might not be the most fundamental state that it could be. So if you give it sufficiently enough time, it would decay into something that are more fundamental.
I think entropy still makes sense when you talk about one particle though, because that one particle can have a bunch of different states to exist in, right? So you can say it has kind of, maybe I'm wrong, I don't know, but my understanding, and again, entropy is like you kind of sum up all the different states something can exist in, and entropy kind of characterizes that. So if you have one particle, it can have different states, so it should still have an entropy.
Yeah, but like the theory that govern entropy also had to deal has a lot of formulation from it are from like building from averages and stuff. So it wouldn't accurately describe the reality if only have 3 particles. Like thermodynamics don't work when you have like 5 particles, right? Like thermodynamic limit actually like really important, not let's say like kind of requirement, but like a restriction that you need to have to for the well, one of the argument that I put against the apple in a box theory was the second law of thermodynamics. That well, I mean, if it decays into something of a higher entropy state or disorder, you can't go from disorder back to order, right? That doesn't sound right. So let's say apple decays into something that's not apple, like into a gloopy blob. But the gloopy blob to recreate an apple, because apple has order, it has low entropy, and to go from higher to low entropy, you need to put in energy. And if the box is isolated, you can't do that. So how can a goopy blob be an apple again? So that's an argument against the argument against that too. So because I look into it more, because like, well, I mean, if you believe in second law of thermodynamics, which hasn't been broken much as many other laws, but there's a claim that it's not absolute either, and I think we can talk about it in a bit. But we talk about the entropy and second law of thermodynamics in our end of the universe, heat death of the universe episode a little bit. Oh, I mean, I think extensively, but I think it's the same idea here that the natural evolution of any system has this type of, well, if you leave it with time, with adding no energy, it always maximizes entropy, and is what we observe, is what we found in the universe, that we believe it anything, any system isolated, it will maximize the entropy. And why would it come back to be an apple? It doesn't make that much sense to me the first time. So there are two conflicting sides to this theory. The first is that, well, okay, we were talking about before that because it's possible to be formed, that the apple's one of the states has to be reused, then because of fluctuations, gradually, this is not fast thing, gradually it would revisit those states. And the second conflicting side, the other side, is that, well, entropy kind of dictates how evolution goes in terms of in the system. So the arrow of time flows one way, and the way it goes is from order to disorder. And if you want to go against the flow, you have to put in energy.
I guess just thinking about this and thinking about energy input and what would happen over time makes me think about the heat death of the universe, where after many trillions and trillions of years, stars will stop fusing. There wouldn't really be any motivation, per se, for any galaxies to form because there's no stars, and there wouldn't really be clumping, so heat will die in the universe where there's not really any transitions happening, if that's a fair way to put that. And so if the universe's time is infinite, would that be kind of like the apple in a box where it will eventually go through all states as well?
Well, actually, I talked about it a little bit with my colleague too. Well, I mean, universe is like apple in a box, but I think we should revisit that a little later once we set up this more, because the argument that they had is not to go against entropy, was that, well, second law of that thermodynamics is not absolute. I was like, whoa, what? Because they work only in statistical. It's a statistical fact. So it works when you have a lot of like ensembles, which means you have a bunch of particles. You have more particles. It doesn't work for when you look at each individual particle. And it's going to make sense. You describe it microscopically using quantum mechanics, right? Like, so that's not average. Well, some they use average, but like, in many body problems, it's different than statistical mechanics. So it's possible if you believe in quantum fluctuations, right? Like for a particle to fluctuate into a lower entropy state, it should be able to, right? Like if you believe in the Heisenberg uncertainty, it can just fluctuate into states that possibly contribute to lower entropy in the system. So it is possible. And then if you have, let's say, 100 particles, right? It is also possible, though unlikely, that all particles would fluctuate to the same, or to all of them fluctuate to all lower entropy states. And to construct an apple is just a configuration. Your particles have to collide a certain way, and that is possible. So, so all these fluctuations is possible to recreate all the tissues in the apple, though unlikely, right? The collisions would create that because it can fluctuate to those states, and it's possible for those tissue to kind of interact a certain way and create cells and cell structure that create apple again. And if it's possible from fluctuations, then with infinite time, it has to revisit it.
Yeah, that's exactly what I was trying to get at, I think, when I was talking about when you have the apple in the box. If you want things to change, you need some kind of interaction. And so technically there's something in that box interacting with the apple. There's the quantum, like the vacuum of space, which is actually described by quantum field theory. And that's the power of the infinite time, I guess, is although these little quantum fluctuations are super unlikely to all suddenly recreate the apple, if you have an infinite time, infinity is this weirdly confusing, powerful thing where if time's infinite, then it's gonna happen at some point. It's like that I forget the name of it, but it's like some thought experiment where if you have a monkey at a typewriter and he's just typing away, if you leave him for an infinite amount of time, because it's an infinite amount of time, he'll eventually recreate all of Shakespeare's works, which is like, even if he's just randomly typing on it without any thought.
Well, on that too, because it's like you know, when you like, if you look at any irrational number, you find all the patterns of numbers, right? Because if it go infinitely, it has to go through all the stuff. It's makes some sense, right? I had another analogy, but I kind of like forgot midway. I had like a brain fart, but I think it's important to recognize that like probability and possibilities are different. Like even though it's possible, it doesn't mean it's probable. But the analogy is like the system has like the very complicated or really difficult trick shot, which is like you see it all the time. In teenagers do these days, they do trick shots, which are very unlikely, but it happens, right? So if you try it long enough, it might happen. So in the same way, it's like if it's possible to reconstruct an apple from all these elementary particles, then you try it, at sufficiently many times, then why wouldn't apple exist again?
The way I think of it, I mean, a mathematician would slap me in the face for saying this because it's mathematically not sound. But the way I think of it is that if you have an infinitely small probability for something to happen, it's probably not going to happen. But then if you give it an infinite amount of time to happen, it's kind of like the infinitely small cancels out the infinitely large, and then you get like a one. So it's going to happen at some point. That's kind of the
Yeah,
way I
it's
think
like
about it.
Murphy's law, right? Anything that can happen will happen because the universe is so big. But we know the universe is not so big
So
compared to what's possible.
yeah, so I don't know if you plan on getting into this now or later, but what Patrick was saying is that it's apple in a box. It kind of sounds like the universe. You can treat the universe as an apple inside of a box, and I think there's an analogy there to like contracting and expanding periodically, kind of like appearing and disappearing universe, maybe.
Well, one thing I want to get to that before universe is time. We say infinite time, but the way to challenge these theories, because like their logic is very sound when you go through it. So you have to challenge the underlying principle or axiom behind it. So one thing that I challenged it was this, how do you find time? What do you mean time? Infinite time? What does that even mean? So So this, if you time think in conventional sense as like a line, timeline, right? Like, oh, it just goes straight, there's something exists outside the system called time. And when time progress, interaction happens, right? It's just like a more conventional sense. But I don't think that's really how it works. Well, I mean, I might get bashed on for this, but so time is change. It has been around for a while since like the Greeks, like Heraclitus and the fire and time. But that's not the point. So time, how do you measure time? You have to measure change. Well, is time a consequence of change or change the consequence of time? So in the apple in a box thing, it's more like change is a consequence of time because time progress, things change. But I would like to point out that, well, it might be the other way around where time is a consequence, is a measure of change. That's why GR works, general relativity works, because what is length? Length, you measure two events, you measure the spatial, well, you could say spatial duration between two points, right? So that's, we call them length, or spatial distance between two events, because you have to have two events to measure length. Well, what is time? It's a temporal length between two events. You might not measure it spatially, but you still have to have two events to measure time. So that's why time in relativity has been used as one of the coordinates, right? Think about it, because time, to measure it, you have to have two events, event A and event B, and the length or duration, I use that interchangeably. The length between two events in temporally, we call them duration or time. So does time progress because like independently, or do we have to measure the change for time to progress, or even like how to define time that way? So let's say if time exists independently, okay, thing fluctuation can happen, okay, right? But if times only progress certain way from change, that change induced time, then if the change that are possible are only the change that goes through higher entropy states, so follow the second law of thermodynamics are the change that actually progress time, then it's not possible to go to lower entropy states because you wouldn't be able to observe the flow of energy fluctuations, because that's not how time progress. Because the time that we see only progress when the thing or the system maximize entropy. That's why we call time. That the lower entropy fluctuations is not observable. Well, I mean, that's a bold claim. Well, it could be true, it could not be true, right? That's why I think it's kind of want to point that out too. Like, how do you define time? Is time just a time like exists outside of the system, or the system changes and that induce time?
I got a little lost in there, I'm not gonna lie. But I think I got the gist of it.
I know it's
Yeah, that's an interesting. This is some like Einstein level thoughts you're having here.
it's easier when I can write them down, right? When I showed to my colleague when I wrote like the thing down, it's easier. But like to just explain is a little difficult. I still haven't really made up my mind around it, so it's not really well polished thought yet. Because like, well, going back to Patrick's point about things in the universe, right? Like, well, if Poincare recurrent theorem holds, or this apple in the box theory holds, then our universe exists in some kind of loop. Because like, it has to revisit like the exact moment. This exact moment that we are talking is some kind of combination of atoms, right? And it's possible in this theory that it has to revisit, if given infinite time or sufficiently long time, it has to revisit this exact moment in this exact configuration that we're talking. All things in the world revolve this way. Then maybe the time in this case exists in some kind of loop, because there's a finite number of atoms in the universe. It's not infinite. Then everything has to be revisited at some point.
Yeah, so this apple in a box thought experiment it's kind of like you have a universe. Eventually there's a heat death, and then since time can go on forever. Well, okay, now I'm getting confused because, well, I guess if there's time can go. You have infinite time, and again, things are changing because you have quantum fluctuation. So I'm trying to think about the analogy you're making between time and change, and then I guess I'm thinking of the apple in a box, like the Big Bang. You get a universe. Eventually, it has a heat death, and again, there's other theories of how the universe ends, but like maybe the heat death is a good one, and then given enough time, you get a Big Bang again. That's kind of like the
Yeah,
apple becomes a blob and eventually it reforms an apple. Although it's not probable it could happen because you're thinking
exactly.
of infinite time.
Even though we say at the heat death nothing can happen, but these quantum fluctuations kind of allow things to happen, right? Like even though it's highly unlikely that in this like barren wasteland of probability that anything would happen at all when everything is so such at a fundamental level, but it's fundamental states, but it's possible for those fundamental to fluctuate into a less fundamental, just tiny less. And if that happened many, many times, then it reconstruct the entire universe.
Of course, that is if the system is isolated. And there are theories that suggest that the universe might not be isolated. I heard one theory a long time ago that dark matter was actually matter from another universe that was colliding with our own. And so there's some pretty far out there theories, but that assumes that the universe is isolated, much like the apple in a box where nothing can get in, nothing can get out. So yeah, lots of big questions here with, okay, well, and lots of, I guess, criteria to ensure that this does happen. But yeah, it's very interesting to think that maybe this has happened already. Like we see the universe is 13.7-ish billion years old, but maybe that's just from when the last Big Bang happened, and maybe it happened before. Maybe it's just time is cyclical, and everything that's happening now has happened again, which means there's been Hyperthesis podcasts before.
Yeah, I wonder how many episodes we got to.
Well, I think this is the time reversal behavior is really interesting to talk about, and it go to the realm of the metaphysical where we can test this, right? Like, so you gotta choose to believe the things that makes most sense to you, or make not even sense sometimes. Like what you want to believe in, right? You want to believe that the world is just like a videotape. I feel old now. Like a videotape. Like it rolls over video and it runs out. Well, it's gonna roll over it again, see the same exact scenes because they're possible. Or you could say that, well, time that we perceive is because of change, and change only progress one way if you don't try to put energy and make it go other ways. There's a natural way that things progress in nature, in not life, in the physical universe. And I think that you can connect that to, let's say, Taoism too, right? There's a way of nature, the Tao, where it's like, oh, this way nature goes. Maybe the way change progress is maximizing entropy. And then if you get to maximal entropy state of the universe, then that's it. However, the apple in a box challenged that, right? Like, well, maybe the change is not absolute in one way. There are fluctuations that can induce the time reversal states that fluctuations can go to the state that it would not naturally go in the in an, like, let's say a bigger system, or like more particles. Like if you talk about average, second law of thermodynamics holds beautifully. But if you talk about each individual particle, why is it impossible that it won't be, that it's able to go to the higher energy states? Because there are fluctuations that make it can go to higher energy states. So there are two sides of the coin, which I'm not sure what to believe. And it's the good part about being scientists is that we are um blasted with many theories and stuff to try to help us make sense of this confusing concept, right? Like I used to believe a lot. Oh, the second law of thermodynamics is absolute. Now that I look at this theory, like maybe it's not. Maybe it's allowed to the fluctuations allow things to happen that not really seems possible practically, but probability is interesting, and infinite time is what's called um gargantual requirement, you know, to have something be infinite, and the power infinity just negate all this impossibly low probability.
That is an interesting thing I want to point out, though, is that you don't necessarily need infinity for this. So if you're looking at the apple in a box and looking at the apple decaying and then going into its elementary particles and then reforming an apple, you just need a very large amount of time, because time is, depending on how you look at it, kind of an countable infinity. But in this case, you can measure the time that takes for the apple to go from its original state to reformation. And yeah, it's just interesting to think that you technically don't need infinite time. And technically, just thinking about it, like, can you ever actually have infinite time that's not theoretical? So same with the universe. Like, if it's an apple in a box as well, then you don't need infinite time for it to reach its state, because it is countable and therefore it's not infinite.
Well, they actually has calculations for it. It's actually I think to revisit the states, like the minimal required time, or like the maximum required time was like, if you live long, what is sufficiently long is e to the power of entropy. So entropy, in the order of like 10 to the 30 for an apple or something like that. So e to the power of 10 to the 30. That's a very large number, right? Like it's huge, and that's like combinatorically large. It's not just large; like it's almost inaccessible in life or in any conceivable notion.
Well, that's something we didn't get into too much. It's like different types of infinities. Because you can think of like 10 to the 10 to the power of 10 to the power of 30 is a huge number, and it's like really massive. Like you can't even comprehend it. But what if you put 10 to the power of that number? Then that number is so much bigger than the previous number, and so there's like infinities are a weird thing. They're hard to think about because or big numbers in general are hard to think about, because you can think this number's so huge that like so many numbers are lower than it, but then there's also an infinite amount of numbers higher than it, even if it's really, really large. And one thing I just want to comment on is in kind of the physics I do, at least, and what a lot of people do, is when we say infinity, we just mean something big. It's you can kind of approximate 10 to the power of 10 to the power of 30 is infinity pretty well. And in these asymptotic calculations I do a lot, you kind of say, you can even say like, oh, 100, yeah, close enough to infinity, depending on the context, which is, mathematicians don't like that, but in certain contexts it makes sense. So yeah, there's all these different types of infinities to think about, which we didn't touch on too much, but this is very interesting to me.
Just to comment on that, even in first year calculus, we use infinities like to calculate where asymptotes are and whatnot, but it's always as it approaches infinity, not equal to infinity, which is interesting. Mm-hmm. But just going back to, I guess, the probability of something happening and the time it will take, like what Feely was mentioning, I'd be very curious to see what that would look like on smaller scales than an apple. So if you had like a couple atoms in, say, crystal lattice of some sort, and then did the calculation, would that be a much more like achievable time? Maybe not within our lifetimes, or even within like the lifetime of the Earth, but is that an experiment that could theoretically be done where you can either run a simulation at a faster speed or measure like very, very small arrangements of atoms or particles and see what happens to them over time?
Well, the problem with that is the setup of the thing. theoretically or on paper, we can discuss this all we want, right? Isolated system, but if you have three particles, you can't isolate it. You want to measure things, you're gonna interact with it at some point. You're gonna put energy into it. Even let's say like, oh, apple in a box. Like, well, what's the box made of? Why is the box don't decay? Well, what happened at the boundary of the box? Well, is there some evanescence or quantum tunneling? Like, things gonna get out or get in, or like how can it not get out or get in, right? Like, and there's a problem of isolating it, and there's a problem with infinite time with isolation. Like, well, if it's possible that the thing can permeate the boundary, like even though it's highly unlikely, but if you give it infinite time, the apple is gonna escape the box.
Yeah, if you were to do an experiment on this, you probably need something. You need one of these ultra cold. The best one I can think of off the top of my head is like ultra cold atomic system. You put a small amount of atoms in this box, but they're always going to be interacting with something, even at like the nano Kelvin range, where there's very, very little like background noise coming in, and there's not like thermal fluctuations. They're still going to have to interact with the box and each other a little bit, and yeah, like this, it's kind of metaphysical in the sense, like you said earlier. It's like I don't think we can ever. I don't know if there's a good way to test this ever, or a good answer that we'll ever come up with.
Yeah, I guess the box itself would be subject to the same decay and whatever the apple experiences. So I guess the best way to experiment with it, or to figure out just if it's possible, is through simulations, which that'd be a very powerful simulation.
One way to do it is to set up such a way that the box has like much larger decay time than the thing you try to observe, right? So I think that's what people do too. Right? You trap certain material in something, well, quote unquote stable materials that like, oh yeah, but we know those stable materials will decay. You trap things in glass, well, or some kind of polymers. Those polymers gonna decay, but it might take 1,000 years. Where what you want to study might take 2 years to decay, right? So you can actually do that. So that might be a way to, but we can test it where the box doesn't contribute enough. But the thing is, like, enough is a loose word, right? You don't know if the boundary of the box, these small interactions would actually create a catastrophic effect or the huge butterfly effect, because you're like trying to test the smallest probabilities. So any other smallest probabilities has to be many order of magnitude smaller, so that it doesn't affect your experiment. But I think we have been talking about it for quite some time. But the point is, I went on this rabbit hole from this one question from my friend's little brother, and it was quite intriguing, and it made me think a lot about my perception of universe, of entropy, of time even. And this kind of investigation helped me sort out through certain things, and not even just for physics, right? I mentioned briefly about Taoism, but also you can think about the concept in time for time in different philosophy, basically, right? How do they perceive the world, or even in terms of like religious belief, or other different type of belief that have on like how the universe will start and end, and well, how do you define time? Can things come back to be itself, or can we revisit time, or like can we travel back in time, right? If states can be reconstructed and time can be reversed, even in tiny scale, well, would it be possible for us to utilize that to go back to time? And there are, well, infinitely many ways to approach this, which I don't think is infinite, but could be. You could also say this: the infinity is the realm of the divine, or the realm of the imagination, the realm of the things we cannot access through measurement. So there are many school of thoughts and arguments in here. But at least for now, I think we can um, stop this here for today, and I'll let Patrick tell everybody how to contact us in this great anniversary and first episode of the season 4.
Yes. So if you would like to contact us, there are many different ways to do so, and there are many different reasons to do so. So the first way that you can contact us is through our Instagram account. We can be found at the Hyperthesis on Instagram, and you can reach out to us, send us a message if you would like to be a guest on our show. We had a lot of guests last season, and hopefully we have a lot more this season. But if you are an expert in your field and you would like to be a guest, you can reach out to us via Instagram. And also, if you're a fan of the show, you can also reach out to us. We recently got a message from a Mr. Plow on Instagram just telling us that they liked our 40th episode and that we should do more on measures. So thank you very much, Mr. Plow, for reaching out. That was very nice to hear your message. So if you have any comments or questions, you can reach out to us via Instagram. That's also where we post updates about shows, as well as some behind the scenes look. Liam did an excellent picture of the three of us. It was a very realistic picture. It was very well done. You can see us possibly in the future. You can also reach out to us over email. We are hyperthesispodcast@gmail.com. We check that very frequently. And so if you have any questions or comments, again, you can find us through email. We are also on, Liam?
Oh, I was just gonna say that giving us ideas and suggestions is always really good. So Mr. Plow, the snow plow guy, because of his message, we're gonna do an episode on measurement in the future. Because it's like, we're interested in it too, right? And we can only come up with so many ideas on our own.
Absolutely.
So the more ideas, the better. Help us out. We are dumb.
Yes, but we love to learn, so we would love to learn more about different topics. We've also uploaded a bunch of videos to YouTube. I think we're up to the end of season 3 now, or just about close to there. So check us out on YouTube as well, and you can share the videos with your friends. You can give us a subscribe there. And of course, if you want to listen to us, you already are listening to us, so thank you for doing that. But we can be found on pretty much any podcasting service available. We are based out of Spotify, which I think is now Spotify for podcasters. It was changed from Anchor FM to Spotify. But we're also on Google Podcast, Apple Podcast, Amazon Music, and again, wherever you find your podcasts. So wherever you listen to us and however you want to reach us, feel free to leave us a comment or questions. Let us know if you want to be a guest on our show. Make sure to subscribe, like, rate, do whatever needs to be done, and especially share our show so that other people can hear it and get some good ideas.
Well, I think lastly, before we get to the story, I want to shout out to Nathaniel Samuel for bringing light to the apple in a box theory to my ears. That makes me think a lot about it. So thank you.
Yes. And continuing on with the idea of maybe not infinity, but very large numbers, today's story will be focusing on finite numbers that are very large and their history, because it's very hard to grasp the concept of things like infinities and countable infinities, which we discussed, like time, where you can count each second going up to infinity, are different than uncountable infinities. So as an example of an uncountable infinity, if you look at numbers between 2 and 3, they're technically an infinite number of numbers that exist between 2 and 3. So 2.01, 2.001, 2.0001. And that's something that's an uncountable infinity because you can just keep going down and down and down. Whereas countable infinities are really interesting and they're actually quite useful in several different applications. And the idea of large numbers is that they're also countable so that we can actually calculate them, we can show them, well, or at least we can theorize how they might be shown, which we'll get into in just a bit. But to go back with very large numbers, we have to go to around 3,000 years ago in ancient India, where there was a written text that contained a list of different names for different powers of 10. Now, these went all the way up to a degree of 12, which we now call a trillion. So 10 to the power of 12, we call a trillion, but there were actually names for this within this ancient Indian manuscript. And they had names for every power of 10, going from 1 all the way up to 10 to the power of 12. And I wouldn't try and pronounce any of these names, and I'm not even sure if the pronunciation is something that's been preserved in different languages. But they consist of a very large range of numbers, especially for the time. At the time, Roman numerals were in use in Rome, and they were a lot clunkier to use. Rome itself, I think, could only go up to something like 100 million in terms of their counting. So going up to a trillion was quite impressive. Now, there were actually other extensive lists of numbers and their names for those different powers of 10 that came from ancient India as well, and a bit more modern India. One of these texts, known as the Lalitavistara Sutra, apologies if I butchered that name, but it gave an even more extensive list of very large numbers, going up to powers of 421. That's 10 to the power of 421, which even today is quite a large number for a lot of people. Now, in this specific text, and also the situation surrounding it, it discussed the idea of expanding geometrically high to higher powers and giving them names. But it didn't go so far as to actually do that, because 421 names for each different power of 10 is quite a lot. And there were even some more texts from ancient India that were a bit later, so more so in the Common Area than before the Common Area, which gave exponents to exponents. And at this point, we had the largest number written down, which was 10 to the power of 10 times 2 to the power of 122. And that 10 times 2 to the power of 122 is all in the exponent of the 10. So again, that's quite a large number. I think that's even larger than the time that it would take for an apple to reconstruct itself in a box, as we discussed earlier. But still, that's a pretty small number. Now, for the time, it was very large. Other civilizations were not really as well versed in large numbers. So ancient Greeks only had numbers up to 100 million, or a myriad. And a myriad was an actual kind of number. And it came around the time of Archimedes, where he also kind of discussed the idea of exponents. However, the Indians were very superior with their inventions of numbers, having invented both negative numbers and zero, both of which are extremely important. They were also actually familiar with the notion of infinity and defined it as a number where the denominator is zero. So this concept of infinity, and especially this kind of calculable infinity, has been around for a long time, and we have the Indians to thank very much for many of the different numbers and the system of numbers that we use. Now, while these large numbers that were brought up many thousands and hundreds of years ago were expressed with exponents, modern mathematicians needed new notations to express these numbers, because you could just keep writing exponents and exponents and exponents, but after a while your hand gets tired, or doing a program to do it, it runs out of memory, things like that. Now, one method that was able to essentially make a shorthand for writing many exponents is tetration, which works on a method of using repeated exponents. So for example, you can have tetration with 2. So it's 2 to the power of 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 2. And it just keeps going for as long as you want, depending on what numbers you use in the notation. Now, this is much more efficient than writing exponents. So you don't have to write 2 to the power of 2 to the power of 2. You can just write the tetrified version, I guess, would be the name of it. But even this isn't able to really express very, very large numbers. So, of course, mathematicians, being who they are, invented new methods to express these large numbers. Now, at this point, it is worth mentioning some very notable large numbers. The first that comes to mind, and might be the most common, is Google, not the giant search engine, but the number GOOGOL, which their name might be based out of, which is 10 to the power of 100. Now, this has been surpassed and is definitely not the largest number, but there are some other notable large numbers, such as the largest known prime number. Now, this may have been updated since the source that I read it from, but it's known as the Mersenne prime, which is 2 to the power of 82,580. No. Yeah, it's 82,589,933 minus 1. So it's the largest prime number that we know of and that we've calculated. I'm sure it's been replaced. I think this is from 2018, but it's quite a large number. And the fact that's prime is super cool. And that gets into a whole debate on an infinite number of prime numbers or not.
The fact that it has -1 is really cool. Just like, they probably try to find a closest even or something, and then just like, oh, well, I'm going to make it odd so they're prime.
Yeah, I think that's how some algorithms do it. But even then, that's not really that big of a number. We have numbers like a Googleplex, which is 10 to the power of 10 to the power of 100, or just 10 to the power of Google, which is an even larger number than that prime number. And then there are other numbers like Squeez's number, which has some very interesting notation. I will not get into it. The notation for some of these numbers is just ridiculous, but it's pure math. So of course, it has to be a bit like that. Now, the largest number for quite a while was Graham's number, which actually won the Guinness World Record for largest number in 1980. But it can't be represented in any way that's communicable by speech.
Graham's number +1 beats it.
and that's the thing with these large numbers, is you can say, okay, but +1 is larger, except for the last one. But just a bit on Graham's number. It was a significant jump in the largest number that could be expressed and determined, but actually requires algorithms to actually express. And just as reference, the number of digits within Graham's number cannot be expressed in the observable universe. So we don't actually have enough information in the universe to express the number of digits that are in the observable universe. So it's a decently large number.
There's a really good YouTube video on Graham's number. It's by, oh God, what are they called again?
Numberphile.
Numberphile, that's it.
Yeah.
I would watch that. It's kind of mind-blowing how big it is.
Yeah, they do a really good job with explaining Graham's number and detailing it out, and it even has its own special symbol. Now, since around 1980, there has been more work into going into larger numbers, and some of the notations involved with this would take several episodes to preface and explain. So there's things like Kruskal's tree theorem, which is complicated. But the current largest number is known as Rayo's number. And this was named after Agustin Rayo, who introduced it in 2007 during a big number duel at MIT. And it was its definition, there's a more technical one, but this definition in English is the smallest number bigger than any finite number named by an expression in the language of first-order set theory with a Google symbols or less. So, that's a lot to unpack. We wouldn't be unpacking all of it, but essentially what it's saying is that there is a specific number that exists that can be expressed using first-order set theory, so not English or Arabic numbers, but using different symbols from set theory, which has a maximum number of letters from this set theory that's under a Google, so under Google symbols, that can be expressed, that is the largest number possible, or at least according to this. Now, this is not a number that we actually know about. We kind of know Graham's number, or at least we know how to represent it, whereas this one is a bit more arbitrary. and it uses just completely different language and notation than what we're used to with exponents. And it's very interesting to think of these kind of abstract concepts of very large numbers, and just the fact that there's an idea of how the largest number could be represented, but it's also extremely difficult to actually represent, is very interesting. So while infinity doesn't really exist, but kind of exist as a tangible result, such as think about just dividing by 0, that approaches infinity as you get closer and closer to 0. And that's how ancient Indian mathematicians were able to express infinity. Expressing very large numbers is a lot more complicated, and it's a very interesting challenge for mathematicians. And it will be interesting to see if there's any future notation that arises from this as they try and go larger and larger and larger.
All right. Thank you, Patrick, for the enlightening story. Infinity is such an important concept, not just in physics, in math, and I think it's a good exercise of thought to anybody. But I think it's a wrap for our first episode of the 4th season, and it's our anniversary episode. So you all have a good day and take care.
Bye, everyone.
See ya.